All right, hello class. Uh, Mr. Pettibone here. So we're gonna just get right into it and continue astrophysics. Um, there's gonna be no daily item today because today's lesson is gonna be um, qualitative. So, hi Michael, hi Spicy Pepper, hi Jackson. Jackson, what's your question? And I'll just look for it in the live chat. I'm going to get started though. So today we're going to talk about basically stellar physics. Okay. Um, Hello, Christian. Um, so, what is a star? Um, and so basically, what you want to think about is a star. In the core of the star, you have nuclear fusion happening. So nuclear fusion is an explosion. Okay. So nuclear fusion is trying to expand the star, make it bigger, puff it out. Okay. Um, but then stars are incredibly massive. So they also have gravity, which is trying to contract the star. Okay. So you have these two competing forces. Okay. You have gravity trying to push the star down to a point. You have nuclear fusion trying to puff the star out. And those two reach an equilibrium at a certain size, and that's what determines the size of a star. Okay? If we were to, for example, make the nuclear fusion more powerful, then explosions are going to get the upper hand and the star is going to puff out a little bit. If gravity were to be made stronger, it's going to contract a little bit. So there's an equilibrium, and stars actually do change size. Okay, but they're relatively stable because what happens is if a star were made bigger, then the core is less dense. And it turns out the nuclear fusion depends sensitively on the density of the core. Okay? So if the star gets bigger and puffs out, the core gets less dense, which reduces the explosive force of the nuclear fusion, which makes gravity scrunch it back down again. Similarly, if gravity scrunches down the star, then that compresses the core, which makes stronger nuclear fusion, which puffs the star back out. So the star's size is stable for that reason. Jackson, I'm going to get to your question at the very end of the lesson, okay? All right, so anyways, you have these two competing factors, okay? So what? And by the way, they're made of mostly hydrogen and to a lesser extent helium. Okay, hydrogen is the most prevalent element in the universe. Helium is the second most prevalent element of the universe. Okay, so there are other elements present in trace amounts, and usually the amount of those other elements is called the metallicity of the star. So, you know, all right. So now I want to talk about what is the life cycle of a star. Okay. So the life cycle of a star, you basically start out with a cloud of gas, and for one reason or another, that cloud of gas has to then start to contract. Okay, and so if you just have a uniform cloud of gas, it's not going to contract. Um, okay. Uh, so it's kind of like you need some kind of something to start the contraction of the gas. So you need some sort of a density irregularity in the gas. So that could be a shock wave traveling through the gas, something like that, that makes one spot higher density than the other spots, and then the gas starts to gravitationally attract towards that higher density spot. And eventually the cloud of gas contracts enough, and as it's contracting, we're releasing gravitational potential energy, which becomes thermal energy. And eventually that thermal energy is enough to ignite nuclear fusion. Okay? And then you have what's called a protostar. So a protostar is a cloud of gas that has nuclear fusion happening in the center, but it's not really like well defined yet. Okay? And once the cloud becomes more or less spherical, then the star will enter what's called the main sequence. And this is where a star spends most of its life, is in the main sequence phase. So the sun is in the main sequence. The main sequence is well over 90% of a star's life. I'm not sure what the exact percentage is, but and the main sequence could last. The main sequence for the sun is going to last for 10 billion years, roughly. The main sequence for larger stars tends to be shorter. So really large stars might only have a main sequence that's a million years or 10 million years or something like that. Small stars have main sequences that are incredibly long. So we're talking trillions of years. Okay, so the length of the main sequence is very dependent on the size of the star. So let me talk about main sequence a little bit. I'm gonna maybe flip the page over and talk about main sequence. In the main sequence, a star is taking hydrogen and fusing it into helium. Okay? So, like I said, the star is made mostly out of hydrogen. So it's taking hydrogen nuclei and shoving them together and making helium. That releases energy. So that's where the energy of the star comes from. All right. And so however long this lasts for, that's the main sequence. Okay. So eventually the core of the star, so the star is always going to be primarily made out of hydrogen. But the core of the star, because that's where the fusion is happening, the core becomes depleted of hydrogen. Okay? All right. So for main sequence stars, we can classify them. And there's a classification scheme, and it's O, B, A, F, G, K, M. Okay, and if you want to remember this, there's a mnemonic to help you remember it. It's O, be a fine girl or guy, whatever your preference is. Kiss me. So that's the mnemonic to help you remember the classification of stars on the main sequence. Now on the O end of the spectrum, these are the really big stars, super duper big. Okay. On the M side of the spectrum is the small stars. All right. Bigger stars tend to burn hotter, and so the O stars tend to be bluer, okay, in color. The M stars are going to be redder. All right, so there's a spectrum. It kind of goes from blue to white to yellow to red. All right. It doesn't go through the rainbow of colors. There's no green stars. It kind of goes from blue to white to orange to red. Let's see. So they're bigger. They're bluer. O-type stars tend to be hotter. M-type stars are cooler. And O-type stars tend to have a short life. M-type stars have long life. So remember, like I said, M-type stars are going to live in their main sequence for trillions of years or more. O-type stars might only be 10 million years or a million years. So huge difference. The sun is a G-type star. Our sun is a G-type star. So that's kind of yellow. All right. Now, what do you think is the most common type of star in the universe? Give you a second to think about it. The most common type of star in the universe is an M-type star. Okay, so basically these O-type stars, they are so short-lived that they do their thing and then they're gone. Okay. So this is the main sequence of stars. Okay. So after the main sequence, the star is going to enter what's called the giant phase. And it's going to be a red giant. So let's talk about the giant phase. So in the giant phase, basically the star is now not fusing hydrogen, but is now fusing helium. Because remember, the core is converting hydrogen into helium, and eventually it doesn't have as much hydrogen anymore, so it starts fusing helium for its explosive force. So it's fusing helium, and helium is more explosive than hydrogen is. More energy is released when helium is burned than when hydrogen is burned. And so going back to the idea that a star is a balancing act between gravity and explosion, then that means that the star all of a sudden gets bigger. Okay? When I say all of a sudden, I don't mean overnight, but over the course of, I don't know how long it happens, but it's probably millions of years. Okay? You could look that up if you're interested. So it's going to puff out. And because the outside of the star is so far away from the interior now, that even though the inside is hotter because helium is more explosive, the outside is actually cooler because it's so far from the core. And so that's why the outside becomes red. So that's why it's called a red giant, because the outside will be red. So the star gets a bigger size. Okay. The star gets a bigger size due to the explosion. It has a cooler exterior. And one thing I wanted to talk about is, guess what the radius of the star will be? The radius of the star, for example, the sun, when the sun enters the red giant phase, the radius will be approximately 1 AU. So that means that basically the Earth will be inside the sun at that point. So again, this is billions of years away. The transition takes, many thousands of years. So it's not going to happen overnight. It's not like we're going to go to sleep and wake up and we're inside the sun. All right. And the other thing I wanted to talk about is the star is actually going to become more luminous. Oh, did I say that too? I should have said that O-type stars are brighter and M-type stars are dimmer. In fact, we have a really hard time even seeing M-type stars because they're so dim. Now, why is a red giant more luminous? Because we have this formula for luminosity. It's sigma A T to the fourth. This is the same formula as power emitted from a black body. And although the exterior's temperature goes down, the surface area of the star, because it is puffed up to such a huge extent, the area goes way, way up and actually overcompensates for the temperature dropping. So the net result is that the luminosity of the star goes up. Okay. Now, depending on the type of star, it can actually kind of like, I'm not an expert in the physics of how this happens, but it is possible for the star to actually have several giant phases and kind of like cycle back and forth. Okay, I think it has to do with something of the motion of gas within the star. So if it becomes a red giant, that can somehow get more hydrogen into the core, so it kind of goes back to the main sequence. All right, so in the red giant phase, it'll fuse hydrogen or helium, and when it fuses helium, I believe it makes carbon, and it'll keep fusing heavier and heavier elements in the giant phase. Okay, but eventually it can't fuse anymore, okay? So what we get is, some kind of an event happens, all right? So maybe... some kind of event is going to happen. So one thing that may happen if it's a low mass star is that it basically just runs out of fuel to fuse, and the star just like goes and shrinks into what is called a white dwarf. Okay, and a white dwarf is basically the ember of a star. So there's no longer any nuclear fusion happening in the core. The only thing that is keeping the white dwarf from collapsing even smaller is the fact that, you know, the material of the star doesn't want to compress any further. Okay, the material resists compression. So you can think about a white dwarf as just the ember of a star. So this is what's going to happen to the sun once it's done with its giant phase. It'll become a white dwarf. And the white dwarf slowly loses energy, or loses its heat, and it becomes a brown dwarf. Okay? So it just slowly cools. White dwarfs are extremely hot initially. Okay? White dwarfs are small. They're roughly Earth-sized. But they're about the same mass as the sun. So they're sun-massed. So they're really dense embers of the star. If it is a high-mass star, then you're going to have an event called a Type 2 supernova. So what happens in a Type 2 supernova is the interior of the star fuses hydrogen into helium, then it fuses helium into carbon, then it fuses carbon into other elements, and eventually you get to iron. Iron is I was wondering what the meaning of that message was. That was a strange message, Michael. Iron is the most stable nucleus, and so you can't fuse past iron. So what happens is, in a Type 2 supernova, is that, and this happens abruptly, okay? The nuclear fusion stops. No more nuclear fusion. So now you have no explosion, so gravity takes over. And the star collapses because there's no explosive force propping it up anymore. And so you have all that gravitational potential energy released. So keep in mind, this is a high mass star. It has tons of gravitational potential energy. Releases that extremely quickly. I'm talking in a matter of seconds. The energy is released. And so a portion of the star gets all of that gravitational potential energy converted into thermal energy and kinetic energy. Okay? Now, it can't be the entire star, because if you release all that gravitational potential energy and it becomes kinetic energy, the star would just puff back out to the same size. So only a portion of the star's mass gets blasted out in a supernova, but there's an explosion, okay? Part of the star gets blasted out at speeds close to the speed of light. Incredible amount of energy is released. And in the case of a Type 2 supernova, one star has the same brightness as the entire galaxy. So these are incredibly luminous events. Keep in mind, there are hundreds of billions of stars in a typical galaxy. So the brightness of the star increases by a factor of 100 billion or a trillion. It gets really bright. It doesn't last forever, but the brightness peaks and then it goes down slowly. There have been times in the history of human civilization where there's been a supernova, and it's so bright that you could actually see it during the daytime. There have been supernovas that are so bright that it looks like a point of light in the sky that's so bright you could hold out a book and read by it at nighttime. So these are incredibly luminous events. That would be for a supernova that happened in our own galaxy, which is supernovas are incredibly rare events because, again, these super high mass stars burn themselves out so quickly. So there's not very many of them. So what's left behind after a supernova? You've got the low mass part. So you have a high mass star. The lower mass group of the high mass stars will become what is called a neutron star. Now, a neutron star is, again, it's about the mass of the sun, has roughly the mass of the sun, but it's about the size of New York City. Okay, so it's even denser than a white dwarf. And so what happens is when the supernova happens, Newton's third law is still true, right? So the exterior of the star gets blasted out, but the interior of the star gets shoved and compressed, okay? And there's so much compression that the electrons get pushed into the protons and they turn into neutrons. So the neutron star becomes as dense, or it becomes all neutrons, okay? Whereas a white dwarf, there isn't enough compression, so the protons and the electrons are separate. They don't get shoved into each other. But in a neutron star, the electrons have been shoved into the protons. Everything is neutron now. The neutron stars often spin extremely fast. They're incredibly dense. When I was a little kid, I had a book on astronomy, and I was always amazed by the fact that they said a spoonful of neutron star material weighs as much as a mountain. So think about that. An entire mountain's compressed into the size of a tablespoon. Okay? Neutron stars, they just do their thing. They slowly cool. Now, after a Type 2 supernova, the high mass stars of the high mass, so this is like the cream of the crop, the high mass of the high mass. For them, there's so much mass that even becoming a neutron star is not enough to prevent the gravitational collapse, okay? And so they become what's called a black hole. So basically, the properties of the material are such that nothing can stop the gravitational collapse, okay? There's too much mass. There's too much inward force. And so it just keeps collapsing. And to be honest, we don't really know what happens beyond the point where it becomes a black hole. We don't know. We don't know if it just continues to collapse to a point or if there is some transition to a new material and that halts the collapse. We need more data. We need to understand more about physics to figure that out. So, but the black hole, the reason it's called a black hole is that light cannot escape. So it just appears black. So we don't, and I'm going to have a lesson just purely about black holes. So we'll talk more about those, but they're, so they're pretty mysterious objects. So yeah, this is the life cycle of a star. So there are several options depending on what the mass of the star is. One thing I wanted to talk about, just really briefly, is that, as I said, main sequence stars can only fuse up to iron. Okay, and so all of the elements that are heavier than iron were created in a supernova explosion. So if you have a gold ring or any silver or anything like that, that material was made in a supernova explosion in the distant past. Okay, for real, that's a real fact. Okay, all the gold that is on the Earth is left over from some supernova that happened before there was even a solar system. So that's crazy for me to think about. So we all own at least a little bit of the product of some supernova. Let's see. I'm trying to think if I'm forgetting anything. I think that's all for now. I wanted to talk about the HR diagram here that I have up. So one of the things you'll notice is it actually has the giant phase on it. So why is the giant phase where it is on the HR diagram? The reason is that giants, remember, the surface of a red giant is cooler, but it's bigger, so it becomes more luminous. So red giants are luminous and cool, which corresponds to the upper right-hand corner of the diagram. They're luminous and cool. If we think about white dwarfs are, again, Earth-sized. They're very small, and so their surface area is small. So they're not very bright, but they're extremely hot. So that's why they're in the lower lower left-hand corner of the diagram. Okay. What would happen if you dropped that spoon? Yeah, I mean, it would make a big dent, I would think. Pretty big dent. So the O phase do go into the giant phase, I believe. This is just sort of a general. There's a lot more detail to this, and if I was an astrophysics major, I would know it. But this is kind of the level of detail that I am aware of. But yeah, there is a lot more detail depending on what is the composition of the star and all kinds of little things like that. I did want to address Jackson's question with the Trend of Galaxies on the. So this is as it relates to yesterday's lesson. And my answer to Jackson's question is that space is expanding everywhere. So every galaxy is expanding away from every other galaxy. So if you can imagine taking the surface of a balloon and putting a bunch of dots on the surface of the balloon, and if each dot was a galaxy, and then inflate the balloon, and what you'll find is that every dot moves away from every other dot. So there is no center to the universe. It's just that the entire thing is expanding. I would recommend you, I know there are some good YouTube videos on this phenomenon, and they have some really cool animations to show you that that Hubble's law and does not, in fact, say that we're at the center of the universe. Okay, so the answer to your question is we are not at the center of the universe. The universe has no center, as far as we know, and I would point you to YouTube videos to find really nice visuals that'll help you understand why. All right, so that's my lesson for